Imagine this scenario. It's a Tuesday afternoon, and an internal auditor walks over to your desk.
Right, just a totally normal, slightly stressful Tuesday.
Exactly. And they want to know exactly why a specific transaction limit was enforced on a massive corporate payment that went out last month.
Which, on the surface, sounds like a really simple question.
It does. I mean, you should just be able to point to a central policy and say, there is the rule. But if you work in a modern enterprise, you know that to actually find that answer, your organization has to embark on this crazy archaeological dig.
No, absolutely. It's never just in one place.
No. First, you're sifting through a dusty Microsoft Word document from some risk committee meeting that happened like 3 years ago.
And half the people in that meeting don't even work there anymore.
Right. Then you are cross-referencing that document with a Python script that's currently being maintained by the web team.
Yeah.
And if that wasn't frustrating enough, you finally have to go find someone who can decipher a COBOL file running on a legacy mainframe that actually, processed the final payment.
You're describing a diagnostic landscape that is entirely fractured. I mean, the core problem here is that the business intent, the policy everyone agreed upon in that risk committee meeting says one thing, but the actual execution is scattered to the wind across a dozen different environments.
And the terrifying part is that this isn't some rare apocalyptic scenario. For most institutions, this is literally just Tuesday. It's this phenomenon known as logic drift.
Logic drift? Yeah, that's the perfect term for it.
It is this inevitable reality where an institution's stated intent slowly but surely diverges from the scattered, messy code that's actually enforcing it. You end up with, well, no single auditable source of truth.
And the gap between what the company thinks it's doing and what the servers are actually doing just grows wider every single day.
Which is a huge compliance nightmare.
Mm.
But for this deep dive, we are going on a mission to fix that fragmentation. We are unpacking your sources today to explore a truly fascinating solution to this exact problem.
It really is a game changer for enterprise architecture.
It is. It's a language called OrbaLang. It's a transpilation-first business logic language created by Luigi Pascal Rondanini. And the promise here is massive. You write your business rules once, ensure that both your auditors and your developers can actually read them, and then you run those exact same rules everywhere.
Everywhere, from your shiny modern microservices all the way down to that dusty legacy mainframe.
Exactly. It's an incredibly ambitious goal.
It is, because to solve logic drift, you can't just build a slightly better spreadsheet or throw a new dashboard at the problem. You have to fundamentally change the relationship between the written policy and the executed code.
Okay, let's unpack this. Because if we are going to understand how OrbaLang actually stops that scattered logic, we first have to look at the root cause. Why does the logic scatter in the first place?
According to the sources, it really all comes down to a symptom of how work itself is organized.
So it's an organizational problem, not just a technical one.
Precisely. The sources introduce us to a concept developed by Luigi Pascal Rondanini called the post-project world. And this is a core part of the broader OrbaOS doctrine.
The post-project world. So what does that actually mean for the day-to-day?
Well, for decades, organizations have relied on project-centric coordination. We all know what that looks like, right? Endless status meetings, ad hoc phases, and project managers manually routing decisions from one inbox to another.
Oh yeah, the classic endless email thread asking for approval on a simple invoice, where like 5 different people have to weigh in before anything moves forward.
Exactly. That human-mediated routing is the bottleneck. It's where the drift happens. The post-project world observes that organizations are shifting away from that model.
Right, because it's just too slow.
It is. So instead, coordination is becoming infrastructure. Work is moving to flow-based coordination. In this world, work moves via explicit automated rules. It is not a project phase dependent on human memory anymore. It's a continuous flow governed by strict logic.
I really like that. It's almost like upgrading a city's traffic system. Instead of relying on a human traffic cop at every single intersection, making these ad hoc, localized routing decisions, which is the old project-centric way you're building something better.
Right, you build a system.
Yeah, OrbaLang builds a governed automated grid of traffic lights.
Yeah.
The coordination just becomes pure infrastructure.
That analogy maps perfectly onto the OrbaOS framework. The framework actually defines 4 foundational layers for any organization. Let's anchor this to a real-world scenario like a bank approving a massive corporate loan.
Perfect. Walk us through the layers.
So the first layer is the values layer. These are the ethical and strategic commitments. For the bank, a value might be We do not lend to fossil fuel companies.
Okay, so that's the high-level philosophy,
Yeah.
the guiding principles.
Exactly. And the second layer is the flow layer. This is where routing rules and state transitions live. This is where you literally specify if the loan is over $10 million, require 3 credit checks and escalate to the VP.
Got it. The actual logic gates.
Right. The third is the intelligence layer, where AI is sensing patterns. So maybe it's scanning the application for subtle signs of fraud that a simple rule might miss.
Okay, and the final layer.
The fourth is the human layer. And in this post-project world, human intervention is reserved strictly for actual judgment, ethics, and high-level escalation, like the VP making the final call on a really borderline application.
And OrbaLang is specifically designed to encode that second layer, right? The flow layer.
Exactly. It is the language of those automated traffic lights you mentioned. It dictates when a condition holds, what action is required, and critically, why it's required, providing all the audit metadata.
But if you don't have a standardized language for that flow layer, your traffic lights are all running on completely different electrical grids. I mean, the web app team uses JavaScript to check the loan size, while the database team uses SQL.
And boom, that brings us right back to logic drift.
Which is exactly why a unified language is so necessary. But, when you hear unified business language, it raises an immediate red flag for most engineers.
Oh, absolutely. It sounds like a trap.
Right, because usually when a vendor promises to centralize all your business rules, what they actually want is to sell you a massive, heavy, proprietary rules engine.
Yep. The dreaded black box.
Exactly. Some huge software package that sits in the middle of your architecture in the cloud, forcing every single transaction to route through their servers. And then they charge you a fraction of a cent every time a rule fires. It's the ultimate vendor lock-in nightmare.
Which is a valid fear. But the documentation is incredibly explicit about what OrbaLang is and what it is not. First of all, it operates under an MIT license, making it completely open source.
That's a huge distinction right off the bat.
It is. But more importantly, it is not a vendor rules engine living in the cloud. And it is not a low-code drag-and-drop user interface either.
The term they use in the sources is transpilation-first. What does that actually look like in practice for a developer?
What's fascinating here is the architectural elegance of this approach. Transpilation first means there is no central server dependency.
Not at all.
None. You write your governance vocabulary as plain text in files with a .orb extension. You commit them to version control in Git, just like any other code your team writes.
Okay, so it lives with the rest of the code base.
Exactly. But when you run those files through the OrbaLang compiler, it doesn't execute the rules for you. Instead, it emits native source code for your specific technology stack.
Oh, I see. So if I'm a web developer working in TypeScript, the compiler hands me a raw TypeScript file containing the exact logic from the policy.
Exactly right.
So I just take that TypeScript, I drop it into my own code base, and I run it on my own servers. I'm not paying a toll to OrbaLang every time a user clicks a button.
You own the execution entirely. The policy lives as text, which is incredibly easy for an auditor to read and track over time. But the output is raw, executable code that your engineers can plug directly into their existing continuous integration pipelines.
That completely eliminates the lock-in problem, because even if you stop using OrbaLang tomorrow, you still have all the generated native code running perfectly on your own infrastructure.
Exactly. You're never held hostage.
So this brings up an interesting tension. If the output is highly complex, native code for a given stack, what does the input, the actual .orba file, look like? Because if this is supposed to be readable by a non-technical compliance officer, it cannot look like C++.
It doesn't. OrbaLang is minimal by design. You are only allowed to write 2 specific types of programs, and the structure is strictly limited to 1 program per file.
So no multi-declaration, sprawling files containing thousands of lines of intertwined logic.
None of that. It forces extreme clarity.
So let's look at those 2 program types. The first program type is a function. From the sources, functions handle pure calculations in deterministic steps.
Right, this is the straightforward math.
Yeah, calculating invoice taxes or figuring out volume discount tiers. You give it typed inputs, it runs through a series of pure conditionals and mathematical assignments, and gives you a typed return value.
Exactly. It's just input, calculation, output. But the second program type is where the actual governance magic happens. These are top-level rules.
Rules, okay. How do those differ from functions?
A rule program isn't just a calculation. It represents a standalone governance policy. The sources provide this great example file named highvaluepayment.orba.
Oh, yeah, I saw that one.
So a rule takes in specific typed inputs like the requested payment amount and the user's role in the company. Then it evaluates a Boolean condition.
Like a simple true or false check.
Exactly. For example, when the payment is over $1 million and the user is just a standard employee.
And if that condition is met, the rule dictates a required action. But it's not a free-form script where the developer can do whatever they want, right?
Right. It utilizes a very strict governance vocabulary. A rule can dictate an action to simply approve, deny, or escalate.
So when the standard employee requests a $1 million transfer, then escalate to the Treasury Department.
Exactly. But if we connect this to the bigger picture, it doesn't stop at just the action. The rule forces the author to attach vital audit metadata directly inside the code structure itself.
Oh, wow. So the documentation is literally part of the code.
Yes. You have to include the reasoning for the rule, the severity level, the specific business owner, and the evidence or policy document it references.
Here's where it gets really interesting from an organizational perspective. Because of this rigid structure, you achieve the ultimate win condition for an enterprise.
Which is what?
A compliance officer and a software engineer can sit down, open the exact same .orba file, and completely understand one another. The compliance officer sees the policy thresholds, the escalation requirement, and the audit trail.
And the engineer sees deterministic logic that will compile into perfectly valid code.
Exactly. It functions as a Rosetta Stone. Because in a traditional setup, the compliance officer writes a 50-page Word document outlining the regulations, throws it over the wall to the engineering team, and the engineers just have to interpret that document and write code from scratch.
And that translation gap is exactly where logic drift begins. By forcing both sides to collaborate on the .orba file, the business intent and the technical execution are permanently locked together.
But wait, if the auditor is looking at a plain text policy, but the mainframe requires raw COBOL and the web app requires TypeScript, there has to be a massive translation engine bridging that gap. How does the compiler ensure the meaning isn't lost in translation across such vastly different technologies?
That is the million-dollar question, and it brings us to the technical architecture of the compiler itself. The entire process relies on something called semantic IR, which stands for internal representation.
Okay, semantic IR. So it's less like translating English directly to French and more like extracting the raw mathematical formula of what the rule is trying to achieve, making it a universal blueprint.
That is an excellent way to conceptualize it. When you feed your .orba file into the compiler, the front end parses it, validates it, and resolves all the data types.
But it doesn't try to instantly turn it into Python or Java, right?
No, not yet. It translates it into the semantic IR. It is the pure canonical meaning of your logic, completely stripped of any specific programming syntax.
And once you have that universal blueprint, you just hand it out to the transpilers.
Well, mostly. But there is a crucial intermediary step before emission, especially for the lower level languages.
Oh, there is?
Yeah. The compiler takes the semantic IR and often lowers it into something called OSAR, or Operational Specific Internal Representation.
Wait, OSI. What does that stand for, and why does the code need to be lowered again if semantic IR is already the pure essence of the rule?
Think of it this way. Semantic IR is the high-level abstract concept of the rule. For instance, check if this user is authorized.
Makes sense.
But a legacy mainframe running COBOL doesn't understand high-level abstract concepts. It only understands primitive operational steps, like how to allocate specific chunks of memory or jump to a basic memory address.
Ah, okay, so it needs it broken down much further.
Exactly. OSAR bridges that gap. It takes the beautiful abstract semantic IR and breaks it down into the gritty, primitive operational building blocks that low-level environments require.
And once it's lowered to OSAR?
Once lowered, the transpilers, which are essentially just generators, know how to map those primitive steps into the final target language syntax.
And the list of targets it can emit is just extensive. From a single .orba file, you can emit native code for Python, TypeScript, Java, C#, Go, and even expression-level SQL for your databases.
Which covers basically the entire modern stack.
Yeah, that alone is incredibly useful. But then you look at the legacy targets. It can generate validated code for COBOL, RPG, ABAPE, and SAS. I mean, COBOL in 2026.
It's wild. But consider the massive amount of quality assurance testing this eliminates.
Oh, I didn't even think about that.
Right. Imagine a Treasury Department that writes a daily limit breach rule in OrbaLang just once. Because of the semantic IR pipeline, That exact same rule can emit a TypeScript validator for their modern web application and a COBOL validator for their legacy mainframe.
That completely eliminates the typical 6-month QA cycle, where you're basically just testing if the web app and the mainframe agree with each other.
Exactly. They are perfectly synchronized from day one. There is zero drift. The web app and the mainframe are enforcing the exact same logic because they were generated from the exact same pure mathematical blueprint.
And the compliance officer only had to sign off on one single file.
It is a profound synchronization of the enterprise.
It sounds almost too good to be true.
Well, transparency is important here. The sources make it very clear that OrbaLang is currently at version 0.3 alpha.
Alpha status. Okay, so it's still early.
Yes. While it has a real compiler, rigorous testing, and continuous integration, it is fundamentally an early adoption tool. The syntax is frozen until version 0.4, but the creators explicitly state you should not treat this as a production-certified complete legacy replacement without conducting your own rigorous organizational validation.
That's fair. It is alpha software, which means you proceed with caution. But beyond its current maturity level, there are massive intentional constraints built into the language itself, things it will categorically refuse to do.
Oh, absolutely. The constraints are very strict.
For example, there are no loops, no for loops, no while loops. There are no early returns from a function. And critically, there is no direct database, file, or network I/O. If you want what programmers call a side effect, you have to use special external hooks.
Let's contextualize what a side effect means here because it's vital to understanding OrbaLang. In programming, a side effect is any time the code reaches out to change something in the real world, like querying an external database, writing to a hard drive, or firing off an email over the network.
And OrbaLang simply won't let you do that natively. It forces you to use an external hook, which essentially just generates an empty stub function in the final code.
Right.
So your host application, whether that's your Python server or your COBOL batch job, has to manually fill in the blank to actually send the email or hit the database.
That's exactly how it works.
Wait, so what does this all mean for a developer? If I can't even write a basic for loop or query a database, isn't this language way too restrictive to actually be useful? How do I build anything real?
I totally get that reaction. That is the most common friction point for developers encountering OrbaLang for the first time. If you evaluate it as a general-purpose programming language, it feels crippled. But this raises an important question. What is the actual goal of this tool?
To stop logic drift across vastly different architectures.
Exactly. So the constraint is not a flaw.
Yeah.
It is the fundamental feature making the whole system work. The documentation contains a definitive design rule. If a feature is hard to map cleanly onto multiple mainstream languages, it does not belong in OrbaLang.
Oh, I see. It has to work universally.
Think about the mechanics of a network call or an infinite loop. If you put a network call inside a business rule, the execution latency on a modern cloud server might be 2 milliseconds.
Sure.
But if you compile that same network call down to a 1980s mainframe, the latency or timeout behavior could be wildly different. The semantic meaning changes based on the hardware.
By stripping out loops and side effects, OrbaLang guarantees that the execution is entirely deterministic. The rule will evaluate exactly the same way, in the exact same amount of time relative to its environment, whether it's running in TypeScript or COBOL.
Precisely. Forced simplicity ensures the logic remains pure and perfectly translatable. You trade the flexibility of doing whatever you want for the ironclad governance and portability of knowing your rule behaves identically everywhere.
So you don't use OrbaLang to build your web server. You use OrbaLang to govern the logic running on your web server.
Exactly. It intentionally delegates all the messy, platform-specific stuff like talking to a database back to the host application. OrbaLang isolates and handles the pure auditable decision, the calculation, the condition, and the required approval.
That makes total sense. So we started this deep dive with an auditor asking a simple question, and an organization scrambling through ancient Word docs and scattered code. OrbaLang steps into that chaos and provides a structural solution.
A really elegant one.
It turns scattered intent into one auditable, governable source of truth. A single file that compliance can read, engineers can review, and compilers can mathematically translate into native code for any environment you run.
If you are dealing with complex regulatory compliance, intricate pricing tiers, or high-stakes risk governance, the ability to trace an executing line of code on a server directly back to an auditable policy text is just invaluable.
And the best part is, you don't have to take our word for it. You can actually experiment with this right now. The call to action from the Orbeos team is incredibly frictionless. You just navigate to lang.orbeos.com/playground,
And a playground requires absolutely zero installation.
which is always nice.
Yeah, the entire OrbaLang compiler, including the parsing, the semantic IR generation, and the transpilation, runs completely client-side directly in your browser.
When you get there, there is a 10-lesson guided tutorial waiting for you. You can see the semantic IR working in real time, adapting as you type your business logic, and you can watch it spit out the corresponding Python or COBOL instantly.
It is the fastest way to understand the power of transpilation-first logic.
Absolutely. Again, you can find that at lang.orbeos.com/playground.
Exploring that playground really crystallizes the shift from the chaotic, ad hoc routing of the old project-centric mindset to the governed, automated flows of the post-project world.
Which brings me to a final thought I want to leave you with. We spent this time talking about the technology, the semantic IR, the legacy targets, the compiler mechanics. But think about the human element of this shift.
The human impact is going to be massive.
Oh, yeah. The post-project world doctrine suggests that complex business governance, approvals, and escalations can be encoded into perfectly auditable automated flows.
Right.
If the machine can perfectly route decisions based on a single source of truth, what happens to the traditional roles of middle management?
That is a very provocative question.
If an entire layer of the corporate hierarchy relies on manually routing those very decisions, checking thresholds, and forwarding emails for approval, well, what do they do when the automated traffic lights turn on and the auditor can just read the code directly? Something to mull over the next time you're gigging through a dusty Word document on a Tuesday afternoon.